Every single one of my graduate students has at least one partner either in industry or academia. So we have collaborations with companies, things like Adobe, Microsoft Research, Pixar, some of the partners that CSAIL has in the ECS department, as well as collaborators all over the world, right? So one of the big pleasures of doing research in my field is that there's this giant community of people that are studying these problems in math departments, computer science departments, even aero-astro. And we really make a point of reaching out to these folks and both inviting visitors to come spend time, tell us about the problems that they care about, and reaching out and visiting to see firsthand how we can be the most useful. It's certainly true that some of our work has made it into like the patent stage, for instance, right? And so I hold patents with Pixar Animation Studios and with the Naval Research Labs. And actually these are two good examples of some of the diverse research we do, right? So the patent with the Naval Research Labs is on face recognition, right? How do you go from the 3D shape of your face to the label of who you are? And then on the other hand, the patent that I hold with Pixar is all about non-photorealistic rendering. So obviously a very different context, right? And non-photorealistic rendering is all about how do you take a scene and make it look like somebody's painted it, or how would you interpret an artist's drawing of a single frame and transfer that to an entire video sequence. So there's obviously a very large diversity in the kind of projects we're studying. The Center for Computational Engineering is an organization at MIT that cuts across a lot of different departments and laboratories, right? And this is a group of professors that are really excited about the low-level number crunching problems that appear in aero-astro, mechanical engineering, computer science, and it's all about how do you come up with stable, very large-scale numerical methods that can deal with computation in the age of big data, in the age of these huge scans and real-world objects that are around us, and have computational systems that can predict things like physics, geometric properties, and so on. Right? So through the Center for Computational Engineering, we regularly invite members of industry and academia to come give talks, to visit with the different research labs, and tell us about the research problems they're excited about. And it's also a way for us to take students that are sort of on the mathematical end of these different application fields, right, and have them interact with each other. I mean, it's certainly true that we have a lot of partnerships with different organizations, and the students and postdocs in my group work on all kinds of different problems that are related to these. So for instance, my postdoc just submitted some research that's all about how do you vectorize line drawings and go from some sketched object to a nice image that you could use in graphic design or eventually in architectural drawing and so on. So that's a good example of a nice project where we started with the basic mathematical tools. In his case, he's studying objects like vector fields and frame fields. And at the end of the day, we're working with artists and engineers to help them digitize the drawings and objects that they're trying to design. I have a graduate student who's studying how do you navigate big databases of shapes. Would be another example of a project that we studied. So in his case, one of the really exciting research challenges in the geometry world has to do with how you have intelligent processing of data when it's actually an object, right? So for instance, in computer-aided design and drafting, right, we have tons of data, millions of models of objects that engineers have very carefully designed, right? Gears and mechanical objects, things inside of your kitchen, furniture, whatever. And the best way that we have to search that kind of data right now is by keyword, right? Just typing a word, and you rely on the engineer to essentially carefully describe whatever it is that they made. We have no way of intelligently navigating an object and saying, oh, that object right there is a refrigerator, and now I can load up these 50 other refrigerators to help you with your design process or to help you navigate and understand what's inside of your data set. So this is a really exciting problem because it can help people, for instance, to design the computer-aided design pipeline in a more intelligent way, right? So right now, I don't know, most people haven't experienced designing a 3D object on their computer, but it's a painful, painful experience, right? I mean, whereas word processing has completely revolutionized the way that we communicate ourselves and write, we very rarely think in 3D on a computer, at least on the consumer end. And one of the really exciting and kind of interesting problems that we think about in our group is, can we leverage the fact that now we have tons of 3D data around us, right? I mean, the new cell phones that are coming out can even sense depth and sense the world in front of you using more information than just a photograph. Can we use that to inspire and change the way that we design 3D shapes? And that requires understanding the shapes that we've had and we've scanned and we've already designed, and then leveraging that information to assist in the creative and engineering processes. And these are completely open challenges, right? So more concretely, I mean, I have one of my students is all about, you know, if I have just a partial scan of some object and I don't have the complete picture and I can't see the back of it, can I either intuit the parts of an object that I haven't seen, or can I use the parts that I've already seen as enough information to help me navigate the world around me? So as you can imagine, the applications of this are immense, right? Everywhere from design and engineering to making things like self-driving cars and robotic equipment that need to navigate the world around them in 3D, right? It's not enough to just understand a single image or a video feed, right? And we want to make algorithms that are both practical and large scale and sort of mathematically grounded, right? And so this is a big theme in our group, is all about understanding how the mathematics of fields like differential geometry, differential equations, optimization, metric geometry come into play in designing really practical and efficient algorithms for these different challenges.